Greetings. So, now we are in for testing how correlation is interpreted using hidden variables and using quantum mechanics. So, how it is done using quantum mechanics is what we just discussed in the previous class. A measure of probability that a certain system is in one of the states is given by the modulus square of the complex coefficient. Okay? And in the previous class we met these terms. So, they involved half the difference angle and their sines and cosines. We have discussed why the half factor comes, why the sine and the cosine comes, and why the difference angle comes, right. And now we will discuss how these correlations can be estimated using some local hidden variables, and then we will ask if these predictions are compatible with the predictions of quantum mechanics. Predictions of quantum mechanics we know are borne out by experiments. Okay. If you carry out experiment, that is what you get. And now we will give take specific clue from these colors which have been given to the apparatus. It is only to build an association which I am going to discuss now. Okay? Otherwise, the magnetic field does not have any color. Okay? And this is what John Bell did in 1964. He set up a mathematical inequality that if this inequality is satisfied, this is the kind of inequality which is satisfied if the local hidden variables can account for the correlation. Okay, so, this becomes a test on the basis of which you can sort of determine if the EPR argument was a strong argument or not, right. And it will turn out that quantum correlations violate this inequality, and you will then be led to the conclusion that quantum theory cannot be both local and counterfactual. So, Bell set up an inequality, a mathematical inequality which must be satisfied by all theories. Any theory which is both local and counterfactual must satisfy this inequality, and I discussed these terms in the previous class as to what is a counterfactual theory, and you are then led to the conclusion that quantum theory is either non-counterfactual or non-local. So, you remember I pointed this out in terms of this Venn diagram, that if you have a theory which is both local and counterfactual, then you are talking about the intersection of the two. And if you are led to the complement of this, which is outside this intersection, then it is either this or that. Okay? So, that is the conclusion we are going to be led to. So, we begin with these three different apparatus which Alice and Bob have, which can be oriented at different angles, and the colors only represent these orientations. Okay, so, the color is, you have a one-to-one mapping between the color and the angle at which the magnetic field is oriented. There is nothing beyond it, and they could use any of the three orientations or any of the three colors. And we now need to do some bookkeeping. Bookkeeping means, okay, what is the result that Alice gets, and we have to record that result. If she gets spin up, she will record it as pass. If she gets spin down, she will record it as fail. Okay, so, this is the bookkeeping vocabulary that we are now going to develop. Okay. If the same event for which Alice has recorded a pass, she gets spin up. If Bob uses his apparatus, but he uses a blue apparatus, which means that he is using a magnetic field which is oriented with respect to the previous, to Alice's field. If he also gets spin up, then he records it as fail. So, this is the pass fail nomenclature, the bookkeeping arrangement that we are going to use. So, if Alice using red gets pass, we can mark it as pass, you can call it as yes or call it as 1. If Bob using blue gets fail, you can mark it as no or 0. So, the 1 or 0 does not matter, yes or no does not matter, pass or fail does not matter, it is just a 2 state. Okay? And you can use north and south, up and down, hell or heaven, anything. Okay? But there are 2 possibilities and these are indicated by pass and fail. And this is particularly nice to know because then we are going to take this vocabulary to 1 and 0 and use the Boolean algebra and then talk about how quantum computers work using the binary 1 and 0 digits, and then what happens when you superpose them and develop quantum computing. Okay? So, it is just a 2 state system 1 and 0. So, here we are going to call it as pass and fail. Okay? And we can record this outcome as Alice first, Bob next, always ladies first. Okay? So, Alice has used red, she gets a pass. Bob has used a blue, he gets a fail, so that is crossed. Okay? So, the first is always Alice, second is always Bob, uncrossed is pass and crossed is fail. So, that is the notation. Clear? Accordingly, we can yes get R B cross, which we have just discussed. We may get G B cross, which means that Alice has used green and she gets a pass, and Bob has used blue and he gets a fail, right. So, you may get RB cross, GB cross, GR cross and so on. So, these are the combinations that you can get, and this is how we will do the bookkeeping, right. So, let me remind you what a counterfactual theory is. We discussed this in our previous class. Counterfactual definiteness is the assumption that not only the measurement you did has a definite answer, but also the measurement that you did not. And this is what Ali was asking at the end of the previous class, that if you do not measure it, does it have a property? It does have a property in a counterfactual theory, but that does not automatically mean that nature accommodates that. So, in a counterfactual theory, it is meaningful to assign a property to a system whether or not you measure it. If you measure it, you have an answer. If you do not measure it, you can still stipulate that an answer exists. The moon is there even if you do not see it. Okay. But unless you do a measurement, you cannot really answer it. So, these are the 2 sides of the debate. Okay. So, let us consider these 3 colors. Okay. We have the green and the blue and the red. So, these are the 3 orientations of the magnetic fields. The green is this patch, the blue is this patch and the red is that patch. All of these patches sit in a square. There is a black piece which we do not care about. Okay? We are not going to worry about that very much. It is just there, let it be there. We will not interfere with that, it will not interfere with us. Ignore it. Okay? Consider the green, the blue and the red areas. The red is a circular area, the blue and green are rectangular. And then if you see, you have a portion here which is part of green but not of blue. Then you have a part of blue which is not a part of red, and you have a part of green which is not a part of red, right? Okay. And these areas, let them represent in your mind the probability of finding, you may say, a pixel. Will it be in the blue side or the red side or the green side? Okay. So, these areas will correspond to these probabilities. And if you look at this and compare these two, it would be obvious to you that green not blue plus blue not red is greater than or equal to green not red. Now, let me pause here for a few seconds so that you can convince yourself. Right? So, green not blue plus blue not red is greater than or equal to green not red. Okay? So, this is an inequality. This is actually the Bell's inequality. Okay? What makes it counterfactual with reference to local hidden variables is because when you say green not blue, it may include green not blue and yes red or green not blue not red. Both the possibilities are there. Okay? Whether or not you measure it. So, if there are local hidden variables that you have not measured, but they are there, and a counterfactual theory will admit them. So, the inequality that we have seen corresponds to green not blue. Similarly, the blue not red will include blue not red with yes green and blue not red with not green. So, the same inequality with added information which were hidden from the previous inequality takes the form that you have at the bottom. Okay? Because what was missing had the whatever was missing in the previous information, it included the third color and it included both parts of the third color, both the appearance and also not being there. So, both R and not R are present in G naught B. G naught B, that space, the space of G naught B, the probability space of G naught B, the area is now giving us a measure of probability. The probability space of G naught B includes G naught B R and also G naught B not R. Okay? And in a counterfactual theory, it is meaningful to assign a property to a system irrespective of whether or not it is measured. And this is the inequality that you expect a counterfactual theory to reflect. Okay? And the probabilities that we get from this. So, if you perform measurements using blue, green and red colors, which are three different quantum apparatuses, right, and then get the correlations from them using a Stern-Gilbert apparatus, and then you can set up a one-to-one correspondence and test this inequality. Okay? Now, this is the marvelous work of John Bell, which is why Stapp said that this is one of the most important pieces of work. Okay? So, this is the prediction of classical correlation. It is contained in this inequality, and if you have an experiment which gives you a result which contradicts it, then it would mean that quantum theory is either non-counterfactual or non-local, and that will give you an ability to conclude and decide on which side of the debate you want to stand, right? And this is what Niels Bohr pointed out in his commentary on the EPR paper, that the arguments of EPR do not justify their conclusion that quantum mechanical description is essentially incomplete. So, incompleteness is not the problem of quantum mechanics. Entanglement is an intrinsic nature of quantum mechanics, and it is not because of any incomplete information. So, that was Bohr's position. You can see it using the Venn diagrams which we have used. So, there are 3 circles, the green, the blue and the red. Again, do not look at these colors and say that this is not exactly red and so on. I used the red to fill that circle and then made it a little transparent so that you can read what is behind it. So, the colors do not look exact, but it does not matter. You can see there are 3 colors, the green, the blue and the red, right. And there are different parts which overlap with one or the other color, and there are parts, each has got a part which overlaps with the other 2, and each also has a part which does not overlap with the other 2, with one of the other, right. So, each section you have written these 7 sections over here and label them as, look at section number 2, which is a part of green, which is a part of blue, but not a part of red. So, it is GB not red, right. Section 4 is G, it is a part of green, it is a part of red, but it is not a part of blue. So, it is G not B red, right. So, each section is double valued in 2 ways. The red may overlap with green or it may not, but also the red may overlap with blue or it may not. Whether it does or not depends on whether you care to carry out that measurement. If you do not carry out that measurement, it still has a piece of information which is sitting there. Okay? So, it is the same with other circles, and we have 3 sets of apparatus, and now we are going to draw one-to-one correspondence between those 3 apparatus, which is why I was coloring them from the very beginning. They did not need those colors, but we are going to use this association now. So, we have 3 sets of apparatus at 3 different orientations, okay? And we may have a decay, and it may result in a pass through green and a fail through red. Okay? So, now we know what we are talking about, we have defined these terms, what is pass and what is fail. Both Alice and Bob may get spin up when they have used respectively green and red apparatus. If that happens, then it will be recorded as pass through green and a fail through red. So, that is the bookkeeping that we are using. So, what you can do is you can keep counting when do they get spin ups and when do they get spin down, what are the probabilities, and maintain a record and then compare the predictions. And in this, the area is of overlap and so on it is a measure of the probability correlation. Okay, it is common to both the apparatus. Is the result common to both the apparatus? Is the spin up common to both the orientations, or only one or the other, to the green apparatus or to the blue apparatus and the red apparatus? So, there were three different apparatuses at three different orientations, corresponding to which we have these three different circles with three colors. Okay. And those correlations we have already discussed in terms of the modulus square of the coefficients of the sine and cosine of the half the difference angles, and here the correlations are indicated by the Bell's inequality. So, here you see that same kind of thing that we did earlier, that the area 1 plus 2 plus 3 plus 4 will be greater than or equal to 1 plus 2. It will be equal only if 3 and 4 go to 0, right. 3 is not G, B not R, right. Otherwise, the inequality will hold, and this is coming from the counterfactual hidden variables. Okay, whether or not you measure those properties, they have a place, and with reference to them you are led to these inequalities. So, you can see it in terms of these square circles or in terms of this other picture, and in both you are led to this inequality. That G naught B plus B naught red is greater than or equal to G naught red. Now, can we compare this result with the correlations that we get from measurements carried out by Bob and Alice using their apparatuses, which are different apparatuses having different orientations, and find if their results, the correlations that we get from their results, agree with the predictions of this inequality? That is the test that we are going to carry out. Okay. And what is important is that G naught B naught red is included in G naught red, because each term in the inequality, it has got the other third color and also not the other third color. So, both of those are present. Okay? So, that is the important point. And we are referring to properties which exist whether or not you measure them. So, this is the inequality that we are going to deal with. So, now I think the whole Bell's inequality is now clear in your mind, right. So, this inequality is what is called as Bell's inequality, means we have simplified the discussion. I have followed Harrison's article from American Journal of Physics, which I have given a reference to. The original arguments are a little more involved. You can read through them, but this discussion will give you sufficient introduction into the subject. So, here you are not going to refer to your bookkeeping, okay, in terms of this pass and fail. So, green not B is pass for green and fail for blue. So, this is G not B, which is pass for green and fail for blue, plus the probability for blue pass and red fail. This must be greater than or equal to this probability for pass in green and fail in red. Okay? So, you can write it in different ways, and we now set up the Stern-Gilrath experiment which Bob and Alice are going to use are 3 different orientations. So, one is the green orientation, which is at 0 degrees with respect to the z axis, which is the original reference frame that we used. The reason it is at 0 degrees is because it is the original reference. Okay. Then we have a similar setup in which Alice and Bob set up their experiments with a z axis which is at 45 degrees with respect to the previous one. So, the half angle that we are going to be concerned with will be 22.5 degrees. Okay. That is the red apparatus. And the third apparatus, which is the blue apparatus or the blue orientation if you like, is set up at 90 degrees with respect to the previous one. So, the half this angle will turn out to be 45 degrees. Okay. So, these are the 3 orientations that we are going to work with. And our question is the following: if the occurrence of Alice getting a spin up and Bob also getting spin up, is it explicable by hidden variables? Because now with these 3 orientations, you can map it one to one with the 3 color circles, right, and test the Bell's inequalities, right, as Einstein would wish, or it is explicable only by quantum mechanics by entanglement as Niels Bohr claimed. So, that is our strategy. So, these are the 3 orientations, okay, and you can select any which orientation, which is why the probabilities come in, okay. And Alice may choose any one of the 3 orientations, Bob can also choose any one of the 3 orientations. And what we are now going to do is, if we are now going to do the bookkeeping using the yes and no, the pass and fail according to this prescription. So, keep this in your mind very carefully. Alice gets a spin up and Bob gets a spin down. Then you record this event as 1, as pass. All right. Okay. If Alice gets spin up and Bob also gets spin up, then it is a fail, or wrong, no or 0, hell or heaven, anything. Okay. It is a 2-state answer, one or the other. So, if they use the same orientations, both use red, both use blue or both use green, so their magnetic fields are aligned, whatever it is, it can be this or this or this, yeah, okay. Then the answer will always be pass, okay, and that is not of great interest. But we analyze the probabilities when they choose different orientations and then see if they correspond to the probabilities we get from quantum mechanics. So, let us say Alice chose red and Bob chose green. You can also have the possibility that Alice chose red and Bob also chose red, and now you have to do all this bookkeeping. There are these different possibilities, you need to consider all of them. Or Alice chose red and Bob chose blue, but in these 3 Alice always chose red, but she could have chosen blue or green, and you have additional possibilities. Okay. So, now let us write the results, and Alice may have chosen red and get a spin up, Bob may have chosen a red and get a spin down, or Bob may have chosen a blue and get a spin down, right. So, these are the different possibilities which are now tabulated here, and you can read this table and interpret it very easily, right. So, there is a lot of information in this table, but you know exactly how to read a column and a row and what information it has, right. So, if Alice chose red and Bob chose green, then this is the combination that you are going to get, okay. and you can get either an up down or an up up or an up down again or an up up, but that also depends on what would be the possibility if they had chosen different orientations, right. So, there are these possibilities, and I have put in this red and green rectangles only those corresponding to Alice choosing red and Bob choosing green, but then you have other combinations. Okay. So, notice that if Alice gets spin up and Bob gets spin down, the result is pass, and this is what is pointed out in the first row. Alice has used red, she gets up, Bob has used green, he gets down, right, and therefore, the result is pass, and I will indicate that by the number 1. Okay. So, now I have tabulated these numbers corresponding to different combinations. Okay. On the previous slide, we had Alice getting spin up using red, Bob getting spin down using green, and the result was pass. So, these are the things that are reflected here, right, and you can map this table, and that gives you a mapping between the correlations predicted by hidden variables, whereas predictions, the correlations which we get from quantum theory, we have already discussed. These are the modulus square of the coefficients. Okay. And from quantum mechanics, the probability of getting up up, which we had on the slide 76 of the previous class, it was the square of the sine of the difference angle, half the difference angle, and of course, there was a 1 over root 2 outside the bracket. So, that square becomes 1/2. Okay. So, you have half sine square theta 1 minus theta 2, which is the same as the probability for the down down, and for the up down and down up, the probabilities were the same. They were given by half the cosine square of theta 1 minus theta 2 by 2, right. So, we have done this using quantum correlations. So, now let us consider the difference angle to be 45. Now, we can actually put numbers. We know what is the sine of 45, what is half the angle, what is the square of that. So, the difference angle is 45, half the difference angle is 22.5, right. The sine of 22.5 is this 0.38, the cosine of 22.5 is 0.92, you can get it from your calculators, right, and you can put these numbers, get the sine square, okay, get the cosine square, got it, right. All this is just 10 seconds on your machine, on your calculator, but the correlations predicted by the local hidden variables and the counterfactual thinking is this, that the pass green not blue plus with the probability blue not red must be greater than or equal to the probability green not red. This is what we get from Bell's inequality, right. So, this is what we expect, and two observers using Stern-Gilroy apparatus, if they carry out measurements on the fragments on opposite sides and then tabulate their results and then compare their pass fail arrays as we have documented them, okay, and indicate what is right and what is wrong, or what has passed and what has failed, or what is 1 and what is 0. And we already agreed when to record it as G not B. Alice is always first, lady is first, right. So, we know what is G not B. So, we tabulate all of this and we expect the Bell's inequality to be satisfied for the choice of these three orientations. One in which the two apparatus are oriented at 45 degrees, first at 0, the second at 45, the first at 45, the second at 90. The difference is still 45 degrees, mind you. Okay? I have chosen in the second setup the blue apparatus at 45 degrees and the red apparatus at 90 degrees. The difference is still 45, but these are different orientations. Okay? That is what gives you the three combinations. And then we consider the quantum probabilities of getting up, up or up, down and so on. So, what are we getting? Are the correlations that we get from Bell's inequalities, are they compatible with quantum correlations? Yes and no, that is the question, and that is going to determine whether the local hidden variables can account for quantum uncertainties. So, this is what you will expect from local hidden variables from a counterfactual theory, right. This is what you will expect, but what is it that quantum mechanics gives you? So, the same thing has been stated in different ways, right, equivalent ways, and what quantum mechanics gives you is the answer is in terms of the modular square of these coefficients which we have discussed in the previous class. And quantum mechanics gives you, if one is oriented at 0 and the second is oriented at 90, then the half the angle 90 is involved, and the square of 45 divided by 2 will give you a 0.25 for this. Okay? And then you determine the other combinations and put it in the Bell's inequalities, and what do you get? The sum of the other two probabilities. Look at the equation at the top. You have apparatus 1 at 0 degrees, apparatus 2 at 45 degrees, right, plus the probability for apparatus 1 at 45 degrees, apparatus 2 at 90 degrees, and you expect this to be greater than or equal to the probability for apparatus 1 at 0 degrees and apparatus 2 at 90 degrees. But from the sine and cosine of half the difference angles, what you get is this adds up to 0.1464, which is less than 0.25 rather than greater than or equal to 0.25, right. So, here you have got numbers, you can't argue against those, right. It is beautiful, right. So, the Bell's inequalities really tell you how to find your way through the Bohr-Einstein debate. And Einstein's position was that there must be hidden variables, that there is some information there whether or not you measure it. And if you go by that idea, you arrive at the Bell's inequality, that there is some information there irrespective of whether you measure it. There are those hidden variables and they have got a certain value, but if you take that into conjecture, then the statistical correlations that you get out of them lead you to certain inequalities between these three different combinations. And this inequality is violated by quantum mechanics. Okay. Predictions of quantum mechanics are not compatible with the assumption that the hidden variables are the cause of quantum uncertainties. Okay. So, the cause of quantum uncertainty is not a hidden, it is not a local hidden variable. Okay. So, all experimental tests of Bell's inequalities, these have been carried out by brilliant physicists. Alan Aspect's experiments were amongst the first ones, and the literature is very exciting. Please go through the original papers which I have not discussed, and what we have discussed should give you a break into the original literature, which is challenging, of course, okay. But my hope is that you will be able to read through that. So, local hidden variables are ruled out, but non-local hidden variables are not ruled out. It is either or, you remember that, how we argued the discussion with reference to the counterfactual and local hidden variables theory. Okay? When you exclude the common intersection part of those two circles, then you have either this or that. So, this is the Bell's inequality, and essentially what we find is that the predictions of quantum mechanics are not compatible, because Bell's inequality would require the left hand side to be less than what is on the right side, but you get a contradiction. Okay? And this is independent of the distance between the two measurements. Okay? We never said that okay, it is 2 millimeters or 20 millimeters or 2 billion light years. The conclusions are independent of the distance between them. Over arbitrary distances, this entanglement holds, and it is this entanglement which becomes a powerful tool in quantum computing. So, the nature of probability in classical mechanics in Mahendra Dhoni's toss is intrinsically different from the nature of probability in quantum mechanics. There it is because of absence of information, local hidden variables played a role there, whereas here you have described the law of nature using entanglement, which is intrinsic to the quantum mechanical description of what we now call as the law of nature. And the reason we call it as a law of nature, more appropriately it should be called as a description of what we observe. Okay? We really do not know what the laws are. But if you describe nature using quantum mechanics, then you get correct results, because if you are an Alice and Bob and you carry out these measurements, this is what you are going to get. And such experiments have been carried out. Every measurement which has been carried out on the basis of quantum mechanics, okay, whether it is measurement of these components of magnetic moments, or measurements of collision cross sections, photonization cross sections, everything that we do is based on this principle of superposition. If you carry out a good experiment, that is what you get right. If you do not get it in agreement with it, then either the experiment was wrong or the theory was wrong, or both are wrong. So, uncertainty is intrinsic to how we describe nature, which is why we say that it is a law of nature, because we do not find any exception to it. More appropriately, it should be called as the description of nature which has always found to be correct, to which no exception has been found. What will happen tomorrow is for time to tell. Yeah, I should mention this reference at the bottom, which is a very nice paper which I will strongly recommend. Their experiment to test local hidden variable theories, another experiment which was proposed by Clauser, Horn, Shimony and Richard Holt, and this leads you to a reformulation of Bell's inequalities, okay, but based on the same idea. but the inequalities are somewhat different in their final form. So, they are called as Cssh inequality, Cssh inequality, which is a new avatar of the Bell's inequality, and that gives you another way of testing local hidden variables as opposed to intrinsic quantum entanglement. So, this is again a very nice paper by Richard Holt and his collaborators. I like to mention this also because I met Richard Holt. He is at the University of Western Ontario, brilliant person, and he has a lecture which is available on the YouTube. If you Google it, I am sure you will find it easily. Please go through it. It is a 1-hour lecture, and you will get some insight into this subject by listening to Richard Holt. So, in the next class, we will use this pass and fail or 0 and 1, okay, using which the Boolean algebra, the logic gates can be discussed, right. And then using these logic gates, you can develop electronic circuits using transistors and develop powerful electronics equipments and build computers to do your calculations. And what is fascinating is what was observed by Deutsch and Feynman. Feynman points out that nature is quantum mechanical. So, you need to build computers which are built on a logic which is not 0 or 1, okay, that you have got a bit and the switch is either on or off. The electronic switch is either on or off. Ultimately, your electronic circuits are going to come out in this form. And the cat is either dead or alive, okay, that is what the switch being on, off and on corresponds to. But then the cat is in a state of superposition of being dead or alive, and the switches need to follow the quantum logic, and then you build quantum logic gates. Once you build quantum logic gates, then you get quantum computing. So, that is what we will make an attempt to introduce in the next class. Okay, thank you.